So this should be the equation. Plus Q is the energy released here. So what is the Q? How to calculate? Mass of uranium 238.0508 minus 234.0436 minus of 4.0026 U. This U is AMU. Or this everywhere U will come. Is that okay? No? U into C square, or nearby everything you write U into C square. I think first problem, no? I'll write U. Just seeing what happened, everything fine. But when you get into calculations, I think you'll be in a big, deep trouble. $238. First we'll add up 234.0. In exam C, 4 decimal places. Don't approximate up, please. I don't know, students, what will happen. So like a approximation, 1 decimal place. I'll remove this. Similarly, approximation. Similar this approximation. Don't do that. You can see these 4 decimal places really matters a lot. Up to say how many decimal places you take here, the more accurate you'll get it. So usually what is the practice in books or exams? Up to 4 decimal places is what they give information. In calculations, what all you get, you can keep it 1 extra, 5th decimal place, and you have to carry on. I think rules, what we have, significant figures, no? Try to apply that. This will be 2 minus 238.0462. We'll subtract these two. Minus of 238.0508. 0.0046 U C square. 1 AMU. 1 AMU is how much? 931.470 mega electron volt by C square into C. C square get cancels. So into 931 point. Don't use calculators. Better make a practice. Better make a practice of okay, this much of energy released. Electron. If you want to convert into joule, you can convert it. Mega 10 to the power of 6 charge of electron 10 to the power of minus 1.6. Then you get in terms of joule. This much of energy is released in this particular reaction. So even now, no, you got some method. No, where you go back to the chemistry. In so many reactions where you are supposed to calculate energy release, there's a method. Just sir, but we don't know AMUs. I think you just gather information, and some of the chemical reactions in chemistry, what happen, they say like energy release, but there the energy release will not be of mega. Sometimes will be milli electron volt. You check it that one. But there's a method of calculating that. So where you'll get millijoule or few joules, that will be very small. So here also what happen, 10 to the power of 6 will come. E what happen, 1.6 into 10 to the power of minus 19. So 10 to the power of minus 13. Sir, it's a very small energy. Okay, time being, let it be. Later we'll see in fission fusion how this small energy is going to help us a lot. This is for one atom, no? Like that in 1 kg multiply, you'll get usually very big amount of energy. And this energy, what will happen? Will be converting to kinetic energy of helium and thorium nucleus. So this Q, you can write it as alpha particle. Then what is the ratio of that? K alpha by kth. I think it depends on mass, no? So this will be 4. The one which is lighter should have more velocity, so which will have more speed, thorium or helium? So I think you apply the conservation of linear momentum. The one which is lighter will have more speed. And they may trouble you with that conditions also. So we have this one. Conservation of like a momentum, from conservation of momentum also you can write it. So 2m alpha k alpha is equal to.
Sir, it should be 284 by 4.
Oh, okay, that one. Yeah, I'll bring that one. Equations, let me bring it here. Squaring this. See this now. K alpha by kth equal to m thorium by m alpha. So this will be 234 approximate by 4. So which will be greater? So who will carry more energy? Alpha particle will carry more energy. Fine. Just small basics, nothing to do with nuclear physics, nothing to do with radioactivity. Nothing to do with that one. Just some logical. So this once radioactivity, so nothing to do with that one. Only